Okay, so here's what we've done so far, right? As of last class, we had established all of these rules. So given an accumulation function in the left-hand column, you have the corresponding rate of change function in closed form, right? How did we develop all of those closed form rules? From the definition. So these are all closed form, but we had to prove that these worked using the definition, okay, which is the open form. Okay, so don't forget that, right? That's important. We have the ability to establish all of these, and in fact, the only way to establish any of these rules is starting from the definition. Hence, why it's the definition. Okay, so today, well, okay, so I'm going to highlight this one thing right here. So we've established, so all of these, like this one and this one, well, sort of that one, this one, these that I'm putting dots next to are functions that are just sort of like, here's the function and here's the rule, right? But then we get to this rule, and it's a function defined using other functions, right? In particular, it's the sum of two functions, okay? And so what I want to sort of draw your attention to is that this is a structurally complex function in the sense that its structure is a sum of two other functions, okay? And so what we're going to do today is look at a different way to combine functions and explore what the corresponding rate of change function will have to be, okay? And so the type of combination of functions that I want to look at is what's known as a composite function, okay? So can anybody help us, like remind us of what a composite function is? We've seen one this semester. So if you can think of the one that we've seen this semester, that would be helpful. And if nobody can think of it, can you think of it? Ah, perfect. Okay, so r of left of x. This is an example of a composite function. What makes it composite? Do you have a? Uh-huh. Okay, so beautiful, right? We've got two functions here. We've got the left of x function, and we've sort of plugged it in, if you will, to this r function, okay? So let's actually see how it worked, right? So we have this left function, okay? And we take x, right, as our input for the whole composition. So we input x into left. And what comes out? What comes out? Left of x, right? So we had a shorthand for that. So I'm just going to call it x sub l, okay? And then what do we do? Or what does this function do, I should say? Takes the left of x as an input now. So even though at this stage, right, at this stage, x sub l is an output, right? It's an output of this left function with x as the input, okay? But then because we're doing this composition, it now takes this left of x as an input to the function r, okay? And so the thing that comes out overall is r of left of x, okay? So that's the example that we've seen this semester. Now I want you to generalize it. So can you explain to your neighbor, maybe draw an illustration of the process for a general composition g of f of x? Okay, so that's just in case it's been a while since you thought about these things. That's how we say it, g of f of x. And sometimes you'll see it written as g circle f, like that. So this is another notation that means g of f of x, okay? So talk to your neighbor and explain the process to each other. All right, so who wants to take a stab at it? Yeah? Okay, so x goes into the function f. Great. Beautiful. Okay, that is exactly how function composition works. Okay, so I'll just say it again to make sure it's on the video, right? So we input x into the function f, and that outputs f of x. Okay, but that output becomes the new input for this function g. So then the output there becomes g of f of x. Okay. So you have to just wrap your brain around the idea that an output of a function can be the input of another function. Okay. So then the following functions can be thought of as compositions of two functions. Okay. So what I'd like you guys to do is for each of these four functions, identify what could be the function f and g, such that g composed with f is the function that's written. Okay. Does that make sense what I'm asking you to do? No? Yes? Can't tell. Yeah, basically so you want to pull it apart to write down two different functions, one that's called g and one that's called f, such that when you compose g with f, you get h of x, or p of x, or v of x, or q of x. So you can work together. This is going to take a few minutes. Figure it out. So guys, there's more than one way to do this for these functions. So if you've already come up with a list of f's and g's for each of these four, challenge yourselves to see if you can come up with another, like a different, like, you know, p of q of x, right? Come up with p of q. You've already got f and g. All right, so I saw some good work. So let's run through some of the possibilities, right? Because there's, like I said, there's more than one way to do this for at least two of them, right? So for h of x, what would you guys like to say is f of x? X cubed minus 5, and g of x is the square root of x, right? And so when you do that composition, g of f of x, right, that's basically saying g of x cubed minus 5 So this is your input now, right? And you put that into your g function, and that gives you exactly what we wanted, right? So there's no need to guess. Well, I mean, you know, you can start with a guess, but then you can check your work, right? There's no reason why you should ever like not have the right answer, right? In the sense that you can always check what you're doing, okay? So what about for P? Is 3x to the 8th, okay? And G would be what? E to the x, okay? So is everybody okay with that? Are we good here? Okay. What about for V? ln of x, and we plug that into the function 1 over x. Great. And then for Q, we plug 1 over x into the function sine of x. Great. Okay. So why was I willing to take 10 minutes of class time to do this? Because this is exactly what you need to be able to do in order to find rate of change functions of composite functions. Okay? So you have to be able to identify the structure. That's what we're doing here. We're identifying the structure of these functions so that when you look at a function like q of x, you're like, oh, that's a composite function. I'm going to have to be careful here. Something interesting is happening, right? Because it's not just sine of x. It's sine of another function, okay? So this was time well spent, hopefully, in the sense that hopefully it raises your awareness that when you look at a composite function, there's something interesting happening, okay? And so then why go through all of this? Well, because so far we've got rules for simple functions. And when I say simple, I just mean things like e to the x, right? There's nothing crazy going on with this input here. And so we've already figured out that the rate of change of g would be what? E to the x, right? Okay, but what happens if I define h of x to be e to the 1 over x? Okay, what's the natural temptation? What would you like to say the derivative is? E to the 1 over x, okay? And so let's just pretend for a second that we haven't just talked about how different composite functions are, okay? And explore what would happen, okay? So let's say that our guess, so we're going to guess that our h of x is e to the 1 over x, okay? So now you're asking yourself, why did Stacy ask me to bring my computer to class today? Okay? Because we can check our answers, right? So if I think the derivative or the rate of change function of h is e to the 1 over x, well, let's do it, okay? So bust out your computers. Now it is the time, okay? And let's go to graphing calculator. Okay, so we have this function, h of x, and it is e to the x, right? So I want to, so I have a guess function. So what do you want to call it? Our guess function for the rate of change, what do you want to call it? G? G for guess? Our guess function is our actual function wasn't e to the x, it was e to the 1 over x. My bad. Okay, so our guess function is that it's the same thing, right? E to the 1 over x, okay? So then I could graph that, okay? But that's not going to do me much good at the moment, because then I'm just going to have a graph of the function that I think is the right rate of change function, right? So how could I actually establish, how would I find the rate of change function for h of x without guessing? How do we find rate of change functions? How do we find the derivative? That's a circular statement. Uh-huh. No. None of that. How do we find rate of change functions, guys? What are you mouthing? The definition. Oh my God, thank you. Okay, so what is the definition for the rate of change function? So I'm going to call it R for rate of change function, right? What is it? So I can't type limit. So, okay, but you know that something's going to get small. So let's go ahead and type in what that something is. I better not use h because h is already a function name. So I'm going to introduce delta x back into our life, okay? And I want that to be able to get really small. So I'm going to let it be big at first, and then I'm going to let it... Wait, what? Oh, so what do you want to call it? We can call it anything. You want to call it K or D? Okay, D will be our slider. Okay, so then the rate of change function is going to be what? But what's f? I don't have an f. So I want to find the rate of change function for my function h. So what is the rate of change? Definition. What's f? I don't have an f. H of x plus d, right, because h is the function name, minus all divided by d, right? Okay, and so now I can graph y equals r of x. Let's not make it that. So let's make it blue, okay? And then g, remember, was our guess function, so we'll make it red, okay? So blue for true, okay? We know that y equals r of x is the rate of change function, right? Because we're creating it using the definition. We can trust this, okay? We can't trust our guess. We're just people, right? So, okay, so we trust r of x. We're hoping g of x works, okay? Do they match? No, but should they? Well, no, but okay, but remember though, D was a slider and I let it start at 1. So that's not actually our exact rate of change function yet. What do I still have to do? Make it small. Okay, so I'm going to make it really, really small. Okay, so now the blue graph is our true graph, right? But it still doesn't match up with the red. Okay, so this was a reasonable guess, but alas, it did not work. Okay, so this e to the 1 over x is in fact not the derivative of e to the 1 over x. Okay, so this is what I meant when I said you can use graphing calculator to check your work. Okay, because all you have to do is type in the function, and once we've done this, it'll be super fast. Okay, so we've done all of the hard work now, right? And so when I have my thing here, so what we've established for sure is that the rate of change of h is not e to the 1 over x, okay? We haven't technically figured out what it is yet. Don't worry, it'll come, okay? But so now I have another function, right? X to the 4th. We know how to find the rate of change of this guy. What is it? 4x cubed, right? What about this guy? Do we know how to find its rate of change function? Technically we do. How do we do it? What a nightmare, right? You'd have to actually multiply this out. X squared plus e to the x times x squared plus e, blah, right? I can't even say it, right? It's so complicated. It's so annoying. Okay, so we don't want to have to do that, right? So then the natural temptation would be to say, oh, well, this looks like g of x, right? So maybe I could just pull down the 4 and take down the power and hope that would work, okay? So that would be our guess again. So let's try it in graphing calculator. So now we've got, what was it? It was like x squared plus e to the x. That's not an x. And then all raised to the 4th, right? And so then our guess would be 4 times this stuff raised to the 3rd, right? And notice that's all I have to change, right, is the function that we're trying to find the rate of change of and what my guess would be. But like the rate of change definition hasn't changed, right? It's the definition. Okay, so that's what's beautiful about it. And so what I can do now is, again, I can press graph, and you can see, you know, that once again, our guess does not actually match up with the true trustworthy function, okay? So, all right, so hopefully I've convinced you that using graphing calculator can help us at least figure out when we're wrong, okay? So now let's actually talk about how we should be thinking about composite functions and just a friendly reminder of rate of change. Okay, so first let's start with the reminder of rate of change. Okay, what does it mean? So if we suppose that a function f has a rate of change function r of f, right, or r sub f, and suppose that the rate of change of f at 6.1 is 3.8, okay, what does that mean? You want to talk to your neighbor about it? Or do you have ideas? Talk to your neighbor. Too much silence. Thoughts? No? Yes. Yeah, what you got? Okay, that is definitely what that says mathematically, but what does it mean? Yeah. No, this isn't talking about the rate of change of the rate of change. Yeah. Okay, so what does it mean to have what does instantaneous rate of change mean? Yeah. Okay, so you guys are doing a really good job of telling me what this sentence says, like verbatim, what it says. So let's talk about what it means, okay? So if you move x a tiny little bit from 6.1, right, so a little change in x close to 6.1, then the value of f will change about 3.8 times as much. Remember, rate of change is talking about the relative size in changes in y to changes in x. So whenever you talk about a rate of change of a function, you have to be talking about two things. You have to be talking about changes in y and changes in x, right? And their relative sizes. That was the whole first 3 weeks of the semester, right? It's still here, hasn't gone away. So, okay, so this is the meaning behind the statement, the rate of change of f at 6.1 is 3.8. This is what it means. Now we can take it a little bit further just to remind ourselves about the big picture, right? Because we've done other stuff with it. We've done this, right? We've done other stuff with this. So you could expand this out and say, oh, okay, well, remember 3.8 is the rate of change of f at 6.1. Okay, so I could replace that. Now the change in f that we're talking about happens, starting at 6.1 and then going a delta x away from that. So the corresponding f values are f of 6.1 plus delta x and then f of 6.1. So the change in f is that difference. Okay. And so then we can rearrange it. Now this is stuff that we talked about, right? This is essentially going back and thinking in terms of new y value equals old y value plus rate of change times change in x, which gives us a little bit of a change in y. So this is new y equals old y plus change in y. We've done this, right? So hopefully this looks at least a little bit familiar. But really, all of this expansion is just an expansion to refresh your memory, okay? But what I really want to concentrate on right now is this idea, okay? So this is the meaning for rate of change of a function at a given point. It tells you the relative size of changes in x, the changes in the function relative to changes in x, okay? So what happens when we knock it up a level and have to deal with composite functions? Okay, so I've got two functions, f and g. The rate of change of f at x, the rate of change of f of x is 5 at the point 6, 27, and the rate of change of g of x is 3 at the point 27, 14. Okay, what is the rate of change of the composite g of f of x with respect to x at x equals 6? Okay, so we're going to work our way through this. Okay, and so again, thinking about the meanings. Okay, so I'm trying to think of the meaning at the moment of. So actually, first I want to just remind you of some notation. So how would I say this? I'd say the rate of change, right? That's one notation, of g of f of x. And you saw this notation in your homework, evaluated at x equals 6. Okay? So that's something that we're trying to figure out right now, but I want to concentrate on the meaning of it. Okay? So we start with a little bit of change in the input near x equals 6, right? So a little bit of change in x near x equals 6. And so what does the composite function do first with x? Where does it go first? I'm not talking about the derivative at the moment. I'm just asking, what does the function g of f of x do with x first? Sends it into f, okay? So if I have a little bit of change in x, that's going to affect a little bit of change in f, okay? And so that's why we have this rate of change of f information up here, okay? So a little bit of change in x is going to cause a little bit of change in f. And it's going to cause the rate of change in this fashion, right? The rate of change of f of x is 5. So that means that a little bit of change in x is going to result in 5 times the change in f, okay? So the output of f changes a little bit. But remember, this is a composite function. So then once you have f done, then you have to plug it into g, right? And so a little bit of change in f as an output of f becomes a little bit of change of the input now for g, right? Because the next thing I'm going to do is plug this into g. So I've got a change in input to my g by a little bit. That's going to correspond to a change in g's output, right? And where did that change come from? Well, that was the rate of change of g is 3. Okay. So overall, we change the input to the composite function by just a little bit, and the end result is a change in the overall output by 15 times as much in this case. Okay. How are we feeling? Feeling groovy? Okay. So that means when we're talking about the rate of change of a composite function, we have to take into account this whole process, right? So we've got the change of the inner part, if you will, times the change in the outer part that depends on what happened to the inner function. Okay, so let's summarize. Okay, this process of taking the derivative of a composite function has a special name. It's called the chain rule. Okay, and so when you have a composition of g and f, the corresponding rate of change function is the rate of change of g with f of x still plugged in, right? So with respect to f of x times the rate of change of f. Okay, so the rate of change of g of f with respect to x is the rate of change of g with respect to f of x times the rate of change of f with respect to x. Okay, so the things to highlight are in that box where it's the rate of change of g with respect to f of x, and then times the rate of change of f just with respect to x. Okay. So in the previous diagram, this is looking at like the little delta x getting expanded to a delta f, and then this part is the delta f expanded to the delta g of f. So when you do the rate of change, or when you find the rate of change of a composition of functions, okay, you have to, and so this is the way that it's presented in textbooks, which is why it's in this order here. But based off of the previous diagram, the way to actually think about it is you change x by a little bit, and so the inner function f will change by a little bit, right? And then that change in f has to sort of like get plugged in, if you will, to the change in g. Okay, so we've got this rate of change of g. So we had our little changes in x that caused a change in f. And then the changes in f, right? So f is what gets plugged into g. That's what influences the changes in g. So then the overall process comes that way. Yes. Yes, we are going to do some examples very shortly. Okay. So then another way that you'll see this written is using the apostrophe notation. Okay. So, but again, the way that you should think of it and the way you should read it is the rate of change of g of f with respect to x is the rate of change of g with respect to f of x times the rate of change of f with respect to x. Okay. Notice that it's not just the product of the rates of change of g with f. It's not how this works. Yeah.
So would it be like a tab that you're continuously hitting an open button and it opens more and more and more?
That sounds reasonable. All right, and again, it's not this because the rate of change of g has to depend on the value of f. Okay, so all of this again, you have to keep in mind. So composition functions are tricky in the sense that like you're plugging in the input into f, and then that gives you a new output. It may or may not have the same value as the original input, but then that new number, whatever it is, gets plugged into your outer function, g, okay? And so like you've got all of these things running around. So I just want to like draw your attention to something I didn't draw your attention to when we first looked at this, right? Because we were concentrating on the rates of f and g. But notice we were looking for the rate of change of g of f with respect to x at x equals 6, okay? So then when we talk about the rate of change of f, I have to talk about that at 6, right, at x equals 6, because that's the function that happens first, okay? But then having this ordered pair means that the output value, so this ordered pair actually means that f of 6 equals 27, right? So then when you look at the rate of change of g, it's going to have 27 as the input, and so that's why I give you the rate of change of g at the point 27, 14, not at like 6, something, right? If I gave you the rate of change of g of x equals 3 at 6, 14, all of this would have been blown out of the water, right? Because you don't look at g when x equals 6. You look at g at f of 6, which is 27, okay? So, so applying the rule that we've got, so the rate of change of the composition is the rate of change of g with respect to f of x times the rate of change of f with respect to x. Okay? So then if I want to do this or find this value when x equals 6, then I look at the rate of change of g with respect to f at 6 times the rate of change of f at 6. Okay? And so this is g, the rate of change of g at f of 6 is 27. The rate of change of f at 6 is 5, right? That's what this equation gave. Yeah.
Is this like our flux problem last night? The flux between 1 and 6?
I don't think so, but I'd have to look at it again. Okay, and so then the rate of change of g at 27, right? So the rate of change of g of x equals 3 at input of 27. So that's 3 times 5 gives us the 15. Okay. All right. So then, let's revisit these two functions, okay? So I've got h of x equals e to the 1 over x. According to the chain rule and some of the work that we've done before, what would be like my f of x for this function h? What would be my inner function? My inner function is 1 over x, which in order to find the rate of change really easily, it's helpful to write it as x to the negative 1. And then my outer function would be e to the x, right? So then the rate of change of h should be so it's the rate of change of g with respect to f. So the rate of change of g is what? E to the x. So if I do the rate of change of g with respect to f, then I get e to the 1 over x, right? But then I have to multiply by the rate of change of f with respect to x, which is what? Negative 1x to the negative 2, right? And so what you can do is take this and type this into graphing calculator now as your guess function and see if it matches up with the true function that we know works from the definition, okay? If I can have your time for just 2 more seconds, maybe 20 more seconds, so we can do one more example. I want to give you guys one more example before I send you home, okay? So taking this function now, I want to find the rate of change of h, okay? So what is the inner function? Great. And the outer function? X to the 4th. So when I find the rate of change of h, I need to take the rate of change of g, but with respect to f. So I still have f, I have to plug f into here, right? So I get 4 times x squared plus e to the x to the 3rd. But then I have to multiply by the rate of change of f, which is what? 2x plus e to the x. So notice these parentheses are really important here because you have to multiply this thing by the whole rate of change of e to the x. Okay. In both, so what I had written up here without simplifying, so this is a simplified version of the rate of change of h up here. And this one doesn't really simplify, but this is the way that I would like you to be finding your rate of change functions. Don't bother simplifying. It's not worth any of our time. Okay? So just leave them as is. All right, have a really good one. You've got homework on Blackboard for Friday. or not on, well, it's posted on Blackboard, but it's my math lab again. Okay.
See the problem.